Hello again. This section and this video are about dynamics, which is the physics of forces and what forces do when they act on things. So we're going to be working with Newton's second law formula, the F equals ma, a fair bit, and probably adding up forces to get a net force, because we pointed out earlier that this formula, even though it's normally written F equals ma, what we're specifically meaning here is F net, as in the total force on an object. Forces are vectors, so they can cancel each other out if they're pushing in opposite directions, or they can add depending if they're going in the same direction. We'll have to pay attention to directions to get these problems right, generally. So, let's get started here. And I apologize, they kind of start out with an ambiguous example here, because they say determine the net force on a 1,000 kilogram rocket accelerating at 5 meters per second squared directly up. My problem with this one is that we normally assume that we're on Earth, where the gravity field is 9.81 newtons per kilogram, but rockets are capable of being out in space where g is a very different number, and so you kind of wonder if they're talking about a space situation or an Earth surface situation. I think what makes me think that it's on Earth is the use of the word up. There is no up in deep space because there is no gravity for you to orient yourself with. So the fact that they're talking about that makes me think, I hope, that we're on the ground, rocket's just preparing to lift off, and so it's sitting on the dirt. And so we do have our 9.81 for G. And that means there are two forces acting on this rocket. Its engine's going to be burning, and so that's going to produce a thrust upward, which I don't want to use T because we often use that for tension in a force problem, so I'll just use F applied for the force from the engines. FE for engine would also have made sense. And the other thing is gravity pulls down on this because it pulls down on everything, so we have a gravitational force going that way. We can find the gravitational force, i.e. the weight, because the weight of anything is its mass times the gravity field it's in. This is a 1,000 kilogram rocket, which is tiny for a rocket. G is 9.81, so we get 9,810 newtons oriented down for a gravitational force, and then we have some force from the engine, and we don't know what that is. And they're telling us that results in the rocket accelerating up at 5 meters per second squared, so Newton's second law, can tie all this together for us. Net force equals mass times acceleration. The net force consists of Fa, don't know what it is, but it still counts, and we have our 9,810 oriented down, so I'm going to put a negative sign on that. In other words, if you want it to be explicit, I'm using the sign convention where up is positive and down is negative. So those two forces together make my net force, the total, and the mass is 1,000 kilograms, and the acceleration is positive 5 upward. 1,000 times 5 is 5,000, so this turns into applied force minus 9,810 equals 5,000. Take the 9810 to the right, and we get applied force is 5,000 plus 9810 is 14,810 newtons. Now that I've done that, I notice that they don't actually want the engine force, they want the net force, so I have wasted a little bit of time here. The net force, it's okay, we can still finish the problem and it won't be too bad, but I worked a little too hard for this. The net force, we said, is the applied force, which is 14,810, plus gravity, which is minus 9,810. Add that up and you get positive 5,000 newtons. They write it as 5 kilonewtons, which means the same thing. So The mistake I made was I worked out this I broke up the net force into engine force and weight, and there was no need for that. We could have just solved for the net force way back here. It would have been net force equals 1,000 times 5. But I don't regret doing this because generally, almost always, we are going to break up the net force into these two pieces, and so you should see that from the very beginning. This thing where we just find the net force is fairly unusual. Most of the time we are interested in finding individual forces. So this is what they asked for, and this is good information, which normally we would have a use for, I promise. Okay. Well, let's try another one and see if my reading comprehension improves. A ball starts at rest and acquires a speed of 12 meters per second when force is applied for a distance of 50 centimeters. Find the magnitude of the applied force. Okay. Let's see. I'm trying to think how many, if there's at least two ways to solve this thing, and the cleanest one is probably to use work energy. We're saying a ball starts at rest, so its initial velocity was 0, and it gets up to a final energy of 12 meters per second. While doing that, it covers a distance of 50 centimeters, which I'm going to write as 0.50 meters. The ball's mass is 1 kilogram, and they want to know how much force was exerted on it. A thing we can do here is, because we know the mass and the velocity, we can find how much energy, kinetic energy, the ball picked up. Kinetic energy is on your formula sheet. It's 1/2 mv squared. 1/2 times what's your mass times how fast did you end up going squared. If we do that for this ball, we get 1/2, the mass is 1, the velocity is 12, don't forget to square it. We find the ball has 72 joules of energy at the end of the motion, and that means this force did 72 joules of work on it. When you do work on something, you either give it energy or you take energy away from it, and in this case, the ball started with no kinetic energy. It was immobile, and it sped up to where it had 72 joules of energy. So we know that the work done by this force, which is force times distance, has to come out to 72 joules. Well, we don't know the force, but we know that the distance was 0.5 meters, and the product of those two has to be 72 joules. Divide by 0.5, and you find that the force is 144 newtons. Now, the reason for this funny answer is all of these data have two significant digits, and that isn't enough to write 144. So if we cut this down to 2 sig-digs, we have two options. We can either say 1.4 times 10 to the 2 newtons, or going to kilonewtons lets us write 0.14 kilonewtons. Either way, we've cut it down to two significant digits so that we're following our precision rules. Fair enough. I want to keep these videos a little shorter than I have been, so I'm going to stop at 2 problems, and if you're interested in number 3, we will see you in the next video.